You ever stop to think about how different programs on your computer actually talk to each other? How does your web browser send a document to your printer? Or how does your word processor even know how to talk to your spell checker? It really does feel like magic, but it's not. It's a core concept in computer science called inter-process communication, and we're about to pull back the curtain on the whole thing.
I mean, think about something you probably do a dozen times a day. Copy and paste. You're literally taking a piece of data from one program, say a web browser, and zapping it over to a totally separate program like your email. How in the world does that information get from point A to point B without just getting lost in the ether? Well, that's the exact question we're going to dig into.
So, the fancy name for this is inter-process communication, or just IPC for short. At its heart, it's just the rulebook, the set of mechanisms that lets different processes, and you can just think of a process as a running program, actually work together. They can share information, they can affect each other's actions, the whole shebang. Okay, but why do we even need programs to cooperate in the first place? Well, for one, pure, raw speed. You can take a massive job, split it up into little pieces, and have different processes chew on them all at once. It's way faster. Secondly, it lets us build things in a smarter way. Modularity. We can create small, specialized programs that do one thing really, really well, and then have them all cooperate. And last but not least, it's the very backbone of how the internet works. That whole client-server model where your browser asks the server for a web page. So how do they actually do it? There are a few ways, but we're going to focus on the two big ones. And first up is the most straightforward, no-frills method, shared memory. The absolute best way to get your head around shared memory is to picture a big public whiteboard, right? Anybody who's in the room can just walk up, grab a marker, and write something on it. Or they can read what someone else already wrote. It's just a common, shared space for everybody. And this is basically what's happening. The operating system's core, the kernel, carves out a little chunk of RAM and says, okay, this is our digital whiteboard. Then it gives both programs, or processes, a key to that room. From that point on, they can read and write directly to that shared space. Notice how they completely bypass the OS for the actual communication. It's super direct, and that makes it incredibly fast. The whole lifecycle here makes a ton of sense. First, one process has to actually request the whiteboard to create that shared space. Then, any other process that wants in has to attach to it, which is kind of like plugging it into its own view of the computer's memory. After that, it's a total free-for-all. They can write and read as much as they need to. And then finally, when they're all done, they detach, and the original process cleans up by destroying the space. And this is where that analogy really pays off. We can map the actual, kind of scary-looking system commands right to our simple whiteboard idea. SMGET, that's just reserving the whiteboard. SMAT, that's giving someone the key to the room. SMDT is when they leave, and SMCTL is calling the janitor to wipe the board and haul it away. See, the entire process is right there in those 4 commands. But if you've ever been in a chaotic meeting, you can probably guess what happens when you give everyone free rein over a single whiteboard. And that brings us to the big, glaring problem with this approach: utter chaos. Here's the catch. The operating system gives you the whiteboard, but it doesn't give you a moderator. There are no rules. It doesn't say who can write, or when, or where. All of that responsibility, all of the work to avoid making a total mess, falls squarely on the shoulders of the programmers. And that is a huge headache. And that leads to the million-dollar question. What actually happens if 2 people walk up to that whiteboard and try to write in the exact same spot at the exact same time? Well, you'd get an unreadable, jumbled mess, right? The same thing happens here. If 2 processes write to the same memory location simultaneously, your data gets corrupted. Game over. So to solve this problem, to prevent this potential chaos, operating systems offer up a second option. It's a much more structured method called message passing. And yeah, it's the organized approach. If shared memory is that chaotic public whiteboard, then message passing is its polar opposite. Think of it like a perfectly organized office mailroom. Instead of scribbling in a shared space, you write a clear, distinct letter. You put it in an envelope and you drop it off at the mailroom for a specific person to pick up. So look at this. The processes never, ever talk to each other directly. Instead, one process uses a send command to give a message to the kernel, our trusty mailroom manager, who holds onto it. Then, whenever the second process is ready, it uses a receive command to go pick it up.
The kernel is the middleman here, making absolutely sure nothing gets lost or overwritten. So what's really going on under the hood? Well, this mailroom is what we call a message queue. It's basically just a list of messages, like letters stacked up in a mailbox, that's completely managed by the OS. When a program sends a new message, it just gets neatly added to the back of the line, waiting patiently to be picked up. No one can scribble over anyone else's letter. It's all very civilized. And hey, just like before, the technical commands line up perfectly with our mailroom analogy. MSGget is what creates the mailroom in the first place. MSSend is the act of sending a letter. MSRCV is you walking up to your mailbox to retrieve your mail. And MSGCTL is for managing things or eventually closing the mailroom down. It's just a much more orderly system. So now we have these two totally different ways for programs to talk to each other, right? The Wild West whiteboard and the super organized mailroom. And this brings us to the bigger picture. How do you choose the right tool for the job?
Let's put them head to head. On one side, you've got the whiteboard, shared memory. It is blazingly fast because there's no middleman. Data just moves. But the risk is huge. It's all on the programmer to prevent chaos. Then you have the mailroom, message passing. It's naturally going to be slower because every single message has to go through the OS kernel, but it's way safer and more structured since the OS handles all the hard parts for you.
And really, that's what it all boils down to. It is the classic engineering trade-off. Do you want raw, unadulterated speed, or do you want built-in safety? Are you willing to manage all that risk yourself for that performance boost? Or is it smarter to take a small performance hit for a system that guarantees things won't blow up? That's the dilemma. And this choice, speed versus safety, it isn't just some problem in a textbook. It's a real balancing act that's happening constantly, deep inside the operating system you're using this very second. So the next time you copy and paste something, just for a second, think about it. Did your computer just use the chaotic, super fast whiteboard or the slower but much safer mailroom?